Proxima Centauri is the nearest star beyond the Sun, and that sounds comforting until you realise what nearest actually means in space. This is our closest stellar neighbour, and even then the distance is so extreme that our fastest spacecraft would need thousands to tens of thousands of years to get there. And that is why Proxima is terrifying, because if this is the easiest star to reach, then the universe is far harsher than most people think. The word nearest is the first trap because your brain hears nearest star and instantly lowers its guard. Nearest sounds like something that is still far but still within reach, still part of a scale you can understand. That is wrong. Proxima Centauri is the closest star to the Sun, and it is still about 4.25 light years away. That is roughly 40.2 trillion kilometers, or about 25 trillion miles. In astronomy, that counts as close. In any human or engineering sense, it is an extreme distance, and that difference is where the whole story starts. You hear closest star, and your instincts quietly translate that into manageable. Not easy, but manageable. Maybe difficult, maybe extensive, maybe a mission for a future civilization, but still the next real target. That instinct fails immediately. The word nearest only makes sense because every other star is even farther away. It does not mean close in the way normal people use the word. It means least far in a setting where everything is staggeringly far. That is why Proxima Centauri is such a brutal reality check. The nearest star beyond the Sun is not sitting just outside the solar system. It is not a slightly longer version of a Mars mission. It is not even in the same category as anything humans have ever travelled to. Once you say the real number out loud, 4.25 light years, the tone has to change. You're no longer talking about ordinary exploration. You're talking about a gap so large that your normal sense of distance becomes useless. And the problem gets worse when you convert that distance into a scale you already know. Proxima is about 268,770 astronomical units away. 1 astronomical unit is the average distance from Earth to the Sun, so the nearest star is more than 250,000 times farther away than Earth is from the Sun. That single comparison destroys everyday thinking. Earth to the Sun is already a distance big enough to define our entire year. Multiply that more than 268,000 times, and now you are looking at the nearest star. That matters because it kills the normal language of travel. Inside the solar system, even when distances are huge, the words still work. You can talk about months, years, launch windows, orbital paths, gravity assists. The missions are difficult, but the scale is still something human beings can organise around. The moment you point toward Proxima Centauri, that changes. Travel stops sounding like a mission and starts sounding like a timescale problem. It starts sounding less like transportation and more like deep time. That is one of the most important things to understand early. Proxima is close by cosmic standards and still basically unreachable by instinct. Your instincts are built from roads, flights, oceans, and maybe planets. They are not built for the space between stars. So when people hear the nearest star, they often do not realise they are already dealing with a distance that has almost nothing in common with anything in ordinary life. And even the nearby stellar neighbourhood is not compact in the way people expect. Proxima is part of the Alpha Centauri system. It is gravitationally bound to Alpha Centauri A and Alpha Centauri B, the brighter pair of stars in that system. That sounds like a nearby little family of stars grouped together in some simple way. But even that picture breaks down when you look at the scale. Proxima still takes more than 500,000 years to orbit Alpha Centauri A and B. That number matters because it shows how misleading your first mental picture is. You hear 3-star system and your brain wants to picture something tidy, something clustered, something where the stars are close enough together to feel like one place. But they are not close in the way you mean close. They are linked by gravity across enormous separation. Even within the nearest stellar system, the distances are so large that stars do not behave like nearby objects. They behave like distant objects that happen to share the same larger structure. So even the nearest stellar neighbourhood is already teaching the same lesson. Space does not scale the way you want it to. A planet can orbit a star at one familiar scale, then another star in the same broader system can sit so far away that its orbital period is longer than the rise and fall of entire species. That is the level of mismatch involved. Human language keeps trying to shrink it into something familiar, and the numbers keep pushing back. Then the real tension appears. Proxima is not only far, it is the best case target. That is the part that makes the distance feel worse, not better. Humanity would choose Proxima first because there is nothing easier. There is no secret nearby star that suddenly makes interstellar travel reasonable. There is no alternate first destination that changes the basic problem. This is the nearest option. This is the least impossible target. That means the first step beyond the solar system is already hard enough to expose a limit in how we think about exploration. If your nearest destination is still separated from you by 40.2 trillion kilometers, then the galaxy is not sitting open in front of us in any practical sense. It exists, we can study it, we can measure it, but reaching it is another matter entirely. The distance to Proxima is not scary because it is an outlier. It is scary because it is the minimum, and that completely changes the meaning of progress. Reaching the moon was hard. Reaching Mars is hard, reaching the outer planets is hard, but all of those still happen inside one system around one star, within a framework where current human civilization can at least attempt the problem. Proxima Centauri sits outside that entire framework. It is the first target that forces you to admit that interstellar travel is not just a more advanced form of space travel, it is a different kind of challenge altogether. That is why the word nearest is such a dangerous word in this story. It sounds comforting, and it should do the opposite. It should warn you that if this is the closest star, then the true scale of the galaxy is much harsher than most people realize. Proxima is not some distant edge case. It is the local example. It is the nearby one. It is the first object that should make human ambition feel small. And once that lands, the next problem gets even worse. Saying 4.25 light-years still sounds abstract to a lot of people. It sounds scientific, but not painful. So the next step is to turn that distance into numbers that stop sounding impressive and start sounding brutal. A light year sounds clean, almost harmless, until you translate it into a number your brain cannot hide from. A lot of people hear light year and think it is a measure of time because the word year is sitting right there. It is not time, it is distance. It is how far light travels in 1 year. And NASA gives that distance as about 9.461 trillion kilometers. So when you say Proxima Centauri is about 4.25 light-years away, you're saying the gap is about 40.2 trillion kilometers, or about 25 trillion miles. That is the real number. That is what the phrase actually means. And once you say that number out loud, the tone changes immediately. This is not decorative science language. This is not one of those facts people throw into documentaries because it sounds advanced. This is the whole problem. Every time you talk about Proxima, you're really talking about the collapse of human-scale thinking. Your instincts are built for streets, cities, countries, maybe at most for the Earth and the Moon if you stretch them hard enough. They are not built for tens of trillions of kilometers. That is why a light year can fool people. The term sounds elegant, almost soft, but the number behind it is violent. 9.461 trillion kilometers for 1 light year, and Proxima is more than 4 of those away. So before you even talk about spacecraft, planets, or missions, you already have a measurement problem. The words sound manageable, but the quantities are not. The phrase feels smooth, the reality is brutal. Then the next question hits, and it hits harder. How big is 40.2 trillion kilometers really? You can say the number, and most people still will not feel it. 25 trillion miles still sounds like just another giant astronomy number. Something so large it almost becomes abstract. So you need a comparison that is simple enough to cut through that numbness. Start with the one distance that secretly runs your whole life, even if you never think about it. Earth goes around the Sun at an average distance of 1 astronomical unit. That is the standard yardstick for the solar system. Earth to Sun, 1 astronomical unit. Mars is a few astronomical units from the Sun depending on where it is in its orbit. Jupiter is about 5 astronomical units. Neptune is about 30 astronomical units. Those are already huge distances by any normal standard. And Proxima Centauri is nearly 268,770 astronomical units away. That is the moment where space is big stops being a cliché and becomes math. Proxima is not a little farther than the planets. It is not even a lot farther in the same sense. It is so much farther away that the entire solar system changes role in your mind. The solar system stops looking like the main stage and starts looking like the front yard. That is how severe the scale jump is. And this matters, because people often assume the problem is that interstellar travel is just a harder version of planetary travel. It is not. The difference is not like going from driving across a city to flying across an ocean. It is more like discovering that everything you thought was the world was actually just your driveway. That is why the number 268,770 astronomical units matters so much. It tells you that you're not talking about a longer route. You're talking about leaving the map entirely. Then the humiliation really starts, because every familiar benchmark fails one after another. In ordinary life, continents feel far apart. Flying across the world feels far. Even within spaceflight, the moon feels far enough to be serious. Mars feels hard, dangerous, expensive. The outer planets feel extreme. Missions there take years, sometimes more than a decade, and that already sounds huge. But the second Proxima enters the picture, all of those distances shrink into local distances. That is not an exaggeration. It is not a dramatic trick. It is what the numbers do. The moon is far in human terms. Mars is far in mission terms. The outer planets are far in solar system terms. Proxima is far in a completely different category. That is the key point. Interstellar distance is not just more distance stacked on top of the same scale. It is a different kind of reality. That is why so many people struggle to feel it properly. Your mind keeps trying to compare Proxima to things it already knows, and every comparison breaks. A city is not enough. A country is not enough. The Earth-Moon gap is not enough. Earth to Mars is not enough. Even the whole width of the planetary system around the Sun is not enough. Proxima sits so far beyond all of those that ordinary language starts to fail. You keep reaching for words like huge, massive, incredible, extreme, and none of them really do the job. And that is also why science fiction can mislead people without even trying to. A lot of sci-fi treats nearby, stars the way people treat nearby countries. Difficult to reach maybe, but still part of the same general world. You point a ship, you travel, you arrive, you deal with whatever is there. Real physics does not give you that kind of convenience. Real physics says that even the nearest stellar destination is so remote that distance becomes the main character of the mission. Once you are dealing with a target like Proxima, the mission is no longer just about pointing a spacecraft in the right direction. It becomes a design problem built around long survival. You have to think about lifetimes, maybe generations depending on the speed. You have to think about systems that operate alone for years or centuries. You have to think about power sources aging, electronics degrading, tiny impact hazards becoming deadly at extreme speed, and communication delays that turn even a simple exchange into a waiting period of years. That is why the distance to Proxima is not just the opening fact of the story, it is the central villain. Every major difficulty grows out of that one number. The propulsion problem comes from it. The communication problem comes from it. The autonomy problem comes from it. The hazard problem comes from it. The reason interstellar travel feels so different from everything humanity has done before is not because the destination is mysterious. It is because the distance is ruthless. And the tension gets worse when you realize that none of this is about some random star on the far side of the galaxy. This is the nearest one. This is the minimum case. This is the shortest possible version of the interstellar problem. So if 4.25 light-years already forces you into numbers this extreme, then the next question becomes unavoidable, and it is even more damaging. If Proxima is 4.25 light-years away, and light itself is the fastest thing in the universe, then how long does even light need to cross the gap? Light itself is slow when the distance is interstellar. And that is where this stops sounding like a hard trip and starts sounding like a different kind of reality. Light is the speed limit of the universe. Nothing with information beats it. Nothing with mass reaches it. And even light needs about 4.25 years to get from Earth to Proxima Centauri. That is the point where the whole subject gets heavier. Not a probe, not a rocket, not some future engine. Light itself needs more than 4 years to cross the gap. That matters because light is absurdly fast on every scale you know. Light can circle Earth more than 7 times in 1 second. It gets from the Sun to Earth in a little over 8 minutes. In everyday terms, it is so fast that it feels instant. And then you put that same light on the route to Proxima, and suddenly instant is gone. Now it is years. Just saying that cleanly changes the mood of the whole story. If the fastest thing in the universe still needs over 4 years, then every other option is automatically worse. That is the point where the distance stops being just a big number and starts changing the rules. Because once light itself looks slow, you are no longer dealing with a normal travel problem. You're dealing with a gap so large that even nature's maximum speed does not make it feel small. And when that lands, another consequence shows up immediately. Communication breaks in a way most people never fully think about. A message to Proxima is not a conversation, it is a time capsule. If you sent a radio signal today, it would take about 4.25 years to arrive. Radio moves at the speed of light, so it gets no special shortcut. If something there replied instantly with 0 delay, that reply would still need another 4.25 years to get back to Earth. That means the fastest possible round-trip exchange is about 8.5 years. That one number changes everything. 8.5 years for the shortest possible hello and response. That is not talking. That is sending history back and forth. You ask a question, then whole governments can change. Whole missions can end. Whole technologies can be replaced before the answer comes back. Even if your communication system is perfect, even if there is no signal loss, no noise, no delay in processing, the gap is still there. The problem is not bandwidth. The problem is space-time. That is why interstellar communication does not behave like a more advanced version of internet, radar, or mission control. It behaves like long-delay exchange between different moments in history. Every message is old when it arrives. Every reply is even older by the time it comes back. So when people casually talk about contacting a probe at another star, it is important to strip the idea down to what it really means. You're not operating a remote machine the way you operate something in Earth orbit. You're pushing information into a void and waiting years to learn what that information did. And once communication slows down that much, control changes meaning completely. A mission to Proxima cannot be flown the way we fly Earth satellites, moon missions, or Mars rovers. There is no live control, there is no joystick, there is no calling and audible in the moment. There is no wait, rotate a little, or stop and check that again, or we found a problem, send a patch now and correct the path. By the time any signal gets there, the situation is already years old. That means interstellar exploration becomes a story about autonomy whether you like it or not. The spacecraft has to make decisions on its own. It has to survive without constant supervision. It has to detect problems, judge conditions, manage power, handle errors, protect itself, and keep going when nobody on Earth can step in fast enough to matter. The further away the mission is, the more that becomes true. At Proxima distance, it is not optional. It is the whole architecture, and that has a deeper effect most people miss. A mission like this may outlast the people who launched it in any meaningful sense. Even if the trip is not thousands of years, the delay alone means the engineers who designed the probe and the scientists who planned its goals may not be the same people interpreting its most important results. Institutions change, priorities change, software standards change. The mission keeps moving anyway. So control is no longer about constant oversight. It is about building a machine and a mission structure that can stay coherent across long gaps in time. That is why the light speed issue is not something you solve, it is something you build around. There is no upgrade that removes it. There is no better antenna that cancels it. There is no cleaner signal that changes the travel time. Light speed is not a technical inconvenience. It is a hard limit built into the structure of the universe. So if you want to send anything to Proxima, you are forced to accept that distance is not just slowing you down physically, it is breaking real-time cause and effect between you and the mission. And that is one of the biggest shifts in the whole story. The distance to Proxima is not just a propulsion problem. It is not only about engines, fuel speed, and travel time, it is a civilization design problem. What kind of species can launch missions it cannot micromanage toward destinations it cannot talk to in real time, knowing that every instruction arrives years late and every answer comes back from an older version of the target? That question matters because it pushes the problem beyond technology. You are now talking about trust in machines, mission planning across decades, scientific patience, and systems that stay useful even when direct human control is impossible. A Mars rover still feels like a machine we are actively operating. A Proxima probe would feel more like a machine we set loose with rules, goals, and judgment, then wait years to hear from. That is a very different relationship between civilization and spacecraft, and it gets even more severe when you realize that all of this, the years of light delay, the loss of real-time control, the need for autonomy, is happening before you even ask the next brutal question. If light takes more than 4 years, then what chance do our fastest actual spacecraft have? Because that is where the situation goes from difficult to savage. Our fastest spacecraft are not even in the same game, and this is where the situation turns brutal. People hear that humanity has probes moving at incredible speed, and they assume that means the first step to another star is already underway. It is not. The numbers look impressive until you put them next to Proxima Centauri, and then the whole thing falls apart. Start with Voyager 1, because Voyager 1 is one of the great symbols of deep space exploration. It is the farthest human-made object from Earth, and relative to the Sun, NASA lists it at about 17.0 kilometers per second, or roughly 38,026.79 miles per hour. That sounds extreme, and on any normal scale it is. It is moving faster than anything in ordinary life by a ridiculous margin. It left the planets behind, it crossed into interstellar space, and it is still one of the most successful machines humanity has ever built. But then you compare that speed to Proxima Centauri, and the illusion dies immediately. At Voyager 1 speed, a straight-line trip to Proxima would take on the order of 75,000 years. Not 75 years, not 750 years, about 75,000 years. That is longer than all of recorded human civilization by far. Agriculture, cities, writing, empires, industry, modern science, all of that fits inside a time span much shorter than the travel time. So the moment you use Voyager as your benchmark, you stop thinking in terms of missions and start thinking in terms of species history. That is the collapse point. Voyager 1 is not some failed machine. It is one of our greatest successes, and even that success is nowhere near what interstellar travel demands. If your champion needs around 75,000 years to reach the nearest star, then the gap between deep space exploration and interstellar travel is not a small gap, it is enormous. Then you go to Parker Solar Probe because Parker is the speed demon of human engineering. At closest approach to the Sun, Parker reaches around 700,000 kilometers per hour, or about 430,000 miles per hour. NASA compares that kind of speed to crossing from Philadelphia to Washington in about a second. On a human scale, that is absurd. It is almost hard to say the number without feeling that it has to be enough for something historic, and yet even Parker barely dents the Proxima problem. If you could somehow point that speed outward and keep it going toward another star, which Parker does not actually do, the trip would still be roughly 6,500 years. That is what makes this so severe. You take one of the fastest spacecraft humans have ever built, moving at a speed that makes ordinary motion look irrelevant, and Proxima still turns it into a journey longer than most civilizations survive. And there is another important detail there. Parker's top speed is not a normal cruise speed for interstellar travel. It gets that speed by diving deep into the Sun's gravity well. It is not a Starship engine steadily pushing a probe across deep space toward another system. so even the 6,500-year figure is already being generous in spirit. It shows how bad the problem is, even when you use one of the most extreme examples available. That is the key emotional point in this whole section. Fast means nothing without context. Human language is terrible at this scale. We say record-breaking, we say blazing through space, we say hurtling. Those words work when you're comparing aircraft, cars, rockets, maybe even missions inside the solar system. But once you bring in interstellar distance, those same words stop helping. They start hiding the truth. A spacecraft can be the fastest thing humanity has ever built and still be hopelessly slow for the trip in front of it. That is not a flaw in the spacecraft. That is the size of the challenge. Proxima does not care how proud we are of our engineering milestones. It does not care that Voyager is historic or that Parker is unbelievably fast by current standards. The distance stays there, and it forces all those achievements into a much harsher perspective. That is why this subject feels so severe once you really face the numbers. Humanity is used to progress looking continuous. You make a better engine, then a better mission, then a faster vehicle, and the frontier moves outward. That pattern works well enough inside the solar system, but with Proxima, that pattern breaks. The step from planetary distances to stellar distances is so large that our current success stories do not look like early versions of interstellar travel. They look like proof of how far away interstellar travel still is, and that leads to a conclusion you cannot avoid. Normal rocketry is not enough. Chemical propulsion does not get you there on meaningful timescales. Gravity assists do not get you there on meaningful timescales. Even our best probes, our fastest probes, our most celebrated probes are still showing the same thing. They are not showing that we are close, they are showing how far short we still are. That does not mean Proxima is beyond physics. It means the kind of propulsion we use now belongs to the wrong class for this problem. It works for launching from Earth, it works for crossing the solar system, it works for incredible robotic exploration around one star. But when the target is 4.25 light years away, those methods stop being a path forward and start becoming a measure of the gap. So Proxima forces a brutal correction. The nearest star is close enough to aim at, close enough to study, close enough to obsess over, but far enough that the entire propulsion logic of current spaceflight starts to look inadequate. Not bad, not disappointing, inadequate at the category level. To get there on timescales that matter to science, institutions, or even a civilization, you need a different class of thinking. And once that lands, another uncomfortable fact appears. Even if you solve the travel speed problem, the destination itself is not a friendly second sun waiting for you. The nearest star is not like our star at all, and that makes the whole story even harsher. Proxima Centauri is not a second sun, and that makes the whole story harder the moment you look at the star itself. A lot of people hear nearest star and quietly picture something like our sun. Maybe a little smaller, maybe a little dimmer, but still basically familiar. That is not what Proxima is. Proxima Centauri is a red dwarf, a faint one, and that changes almost everything about the environment around it. It is not a bright yellow star with a wide, comfortable system built on the same pattern as ours. It is much smaller and much dimmer. NASA and ESA both note that it has only about 1/8 the mass of the Sun, and its average luminosity is very low. That means the nearest star is not a second version of home. It is a different kind of star with a different kind of planetary setting, and the difference matters immediately. The word nearest can mislead you again here, because it makes people expect visibility, brightness, and obvious presence. But near does not mean bright. Proxima is so faint that you cannot see it with the naked eye from Earth, even though it is our nearest stellar neighbour. That alone should reset your sense of scale. The nearest star beyond the Sun does not stand out in the sky as some obvious beacon. It is there, it is local by cosmic standards, and human eyes still miss it completely. That is one of the strangest facts in the whole story. You would think the nearest star beyond the Sun should dominate its patch of sky. You would think it should be one of the most obvious objects overhead. It is not. Hubble sees it as a point-like source. NASA points out that even this nearby star still hints at the huge scale around us because it does not suddenly turn into some giant bright marker just because it is the closest one. The nearest star is still faint enough to hide from ordinary human senses, and that matters for more than just appearances, because the star's smallness squeezes the whole system inward. Since Proxima is cooler and dimmer than the Sun, any orbit that gets Earth-like levels of warmth has to sit much closer to the star. That changes the geometry of everything. Around the Sun, a planet like Earth can sit at a comfortable distance and take a year to orbit. Around Proxima, a potentially temperate planet has to move in tight, close and fast. That is where the whole drama starts to compress. The nearest known Earth mass-like world in that system is not sitting in some broad Earth-Sun style layout. It is tucked very close to a dim red dwarf, inside a compact system where orbital periods are measured in days, not years. So even before you ask whether a planet there could support life, the setup is already more extreme than most people expect. The distances inside the system are smaller, the timing is faster, and the star has much more control over what happens to any nearby world. That is one of the key things a red dwarf changes. A planet can be in the habitable zone in the simple energy sense, meaning it gets the right amount of starlight for liquid water under the right conditions, and still be living in a much harsher arrangement than Earth. Around a red dwarf like Proxima, the habitable zone is pulled in close. That brings planets near the place where stellar flares, radiation, magnetic activity, and tidal effects become much more serious. So the nearest star is not only far away, it is also the wrong kind of familiar. It sounds like the obvious place to look for a second Earth, but the star itself is already warning you that this is not a second solar system waiting to be found. It is a tighter, stranger, more intense environment built around a smaller and less stable kind of sun. And then the stakes get bigger, because Proxima is not some rare exception. It is not a weird one-off that you can safely treat as unusual. Red dwarfs are common. NASA notes that for every star like the Sun, there are roughly 10 red dwarfs. That means Proxima is not just one destination. It is a preview of the kind of destination the galaxy mostly offers. That changes the meaning of the whole topic. This is not just about whether we could ever reach one nearby star. It is also about whether the most common stars in the Milky Way are the kind of places where planets can stay stable, keep atmospheres, and maybe support life. If humanity ever becomes interstellar, it may spend a lot of time dealing with red dwarf systems, not sun-like systems. Proxima is important partly because it is near, but also because it may represent the kind of star we are most likely to encounter again and again. So the nearest star is already doing two things at once. It is showing you how hard interstellar distance is, and it is showing you that even the most common stellar destinations may not look welcoming. Small, dim stars sound less dramatic than giant, bright ones, but for planets nearby, they can create some of the most difficult conditions in the story. And once that sinks in, the picture gets even stranger. Proxima is not sitting alone out there. The nearest star is part of a 3-star neighbourhood, and even that neighbourhood does not feel anything like the compact system people expect. Proxima lives in a 3-star neighbourhood that still feels empty, and that makes the nearest stellar system even stranger than most people expect. A lot of people hear the nearest star system and picture one star with maybe a few planets around it, something simple and self-contained. That is not what is sitting next door. Proxima Centauri is part of the Alpha Centauri system. It is gravitationally bound to Alpha Centauri A and Alpha Centauri B, the bright binary pair that people have known about for a long time. NASA describes the whole thing as a triple star system, with Proxima as the faint red dwarf companion. So the nearest stellar system is not one star in one clean location. It is a structure with 2 sun-like stars and 1 flare-prone red dwarf, all linked together across huge distances. That matters because even when you finally get out of the solar system in your mind, the next thing waiting for you is not simplicity. It is already a more complicated layout than people assume. Then the scale problem comes back immediately. Alpha Centauri A and B are close to each other by stellar standards, but not by yours. They orbit each other in about 80 years, and NASA notes that their characteristic separation is around 23 times the Earth-Sun distance, with that spacing changing as they move through their orbit. Even that central pair already spans a region roughly comparable to the outer solar system. So even before Proxima enters the picture, the main part of Alpha Centauri is already large on a scale that would feel extreme to us. And then Proxima sits far beyond that pair. That is what makes the whole nearest neighbourhood feel so strange. Instead of one tidy compact system, you get something more spread out, more diluted, more like a loose gravitational arrangement than the kind of close grouping people imagine when they hear the word system. The stars are connected, yes, but not in the neat way planets are connected around a single star. The structure is real, but it is stretched across deep space. That becomes much clearer when you look at the distance between Proxima and Alpha Centauri A and B. NASA's Hubble material notes that Proxima is about 0.2 light years from the brighter binary. That is inside the same star system. That is the part that should really reset your expectations. Even inside one system, the stars are not clustered together in some compact, easy-to-picture arrangement. They are separated by a gulf that is enormous by solar system standards. That distance is hard to overstate. By planetary standards, 0.2 light-years is massive. It is not a little extra spacing at the edge of the system. It is a huge separation. So the nearest stellar family is already teaching you something important about how stars actually exist in space. They do not necessarily sit packed together in a way that feels visually or emotionally compact to humans. They can be bound to each other and still live very far apart. That is why the Alpha Centauri system feels both crowded and empty at the same time. On paper, it is a 3-star system. That sounds rich, active, almost dense. But when you look at the actual spacing, the emotional effect flips. It feels sparse, it feels stretched. It feels like even when gravity ties stars together, space still keeps them at a distance that would completely dominate any human way of thinking. And then the timescale makes it even harsher. NASA says Proxima takes more than 500,000 years to orbit Alpha Centauri A and B, more than 500,000 years for one orbit around its stellar companions. That number breaks any normal narrative immediately. You cannot fit it into ordinary history. You cannot fit it into civilization. You cannot fit it into anything most people naturally use to think about time. A full orbital cycle for Proxima outlasts empires, languages, climate shifts, and maybe whole phases of human existence. That is what makes the number so severe. It reminds you that stellar motion is not just slow. It operates on timescales that barely care whether civilizations rise and fall underneath them. Human history is a brief event compared to 1 year in this wider system. That is one of the hardest adjustments in the whole story. People often assume the nearest star system should feel more local, more immediate, more understandable. But the more detail you add, the less familiar it becomes. It is not just that Proxima is far from us. It is that even Proxima's relationship to its own companion stars is defined by distances and timescales that make human life look very small. So the nearest stellar neighbourhood already destroys 2 comforting assumptions at once. First, it shows that nearby does not mean simple. Second, it shows that being in the same system does not mean being close in the way we usually mean close. Alpha Centauri. A and B may form the bright centre. Proxima may be the red dwarf companion, but the whole arrangement is spread across such enormous separations that the word neighbourhood starts to feel misleading again. And that creates a deeper tension. We keep talking about these distances with confidence, which raises an obvious question. If everything out there is so huge, so spread out and so hard to picture, how do we know the distance so precisely in the first place? How do we know Proxima is really there, really that far away, and not just making the sky look flat and static from our point of view? We know the distance because the star betrays itself in motion. That is one of the strongest parts of this whole story, because the distance to Proxima is not a guess. And it is not some old rough estimate that people repeat because it sounds good. It is measured. The key idea is parallax. When your viewpoint changes, a nearby object appears to shift against a much more distant background. That is basic geometry, and astronomy uses that same rule on the sky. NASA's New Horizons team showed this in a very direct way by imaging Proxima from deep in the solar system and comparing how its position looked from that distant viewpoint versus from Earth. The star shifts, and that shift gives you distance. That matters because it turns the nearest star from a vague point of light into something you can measure with geometry. You're not just saying it looks nearby, you're using perspective. Move far enough, look again, and the nearest stars slide relative to the far background. That is how distance to stars begins. Not with mythology, not with guesswork, but with angle, baseline and measurement. Once that lands, Proxima stops being a dramatic idea and starts being a mapped object in space, and New Horizons made that idea feel almost physical. In 2020, NASA described New Horizons viewing Proxima from more than 7 billion kilometers, or 4.3 billion miles from Earth. That created the largest parallax baseline ever used in such an easy-to-see demonstration. That is a huge gift for understanding this subject because it takes parallax out of the textbook and makes it real. Move far enough through space and even the nearest stars stop looking fixed. They slide against the background under the rules of perspective. That is the point where distance becomes something you can almost feel. The spacecraft was so far from Earth that the view of the local stars actually changed in a visible way. So when people talk about the distance to Proxima, it is worth being very clear about what that means. We are not treating the sky like a flat picture and making hopeful assumptions. We are looking from different places, seeing the star shift, and reading distance out of geometry. That is why the number is so powerful. It is not just impressive, it is earned. Then modern precision takes this to another level. Hubble and Gaia turned nearby space into a measured landscape. NASA's Hubble material on Proxima's close sky encounters shows that astronomers can track tiny positional changes with extremely high precision. And ESA's astrometry material explains that milliarc-second accuracy is achievable in space-based measurements. That is a very small angle, far smaller than anything human senses can deal with directly. But it is enough to map nearby stars with extraordinary detail. That is one of the most important realities checks in the whole topic. The distance to Proxima is not some rough story left over from early astronomy. It sits inside a precision map of the local galaxy, built from tiny angular measurements, repeated observations, and careful tracking of motion over time. The nearest star is not just known in a general sense. Its position, shift, and path are measured well enough that astronomers can predict very specific future alignments. That is where astronomy stops sounding broad and starts sounding exact. And Proxima is close enough that its motion is obvious on human timescales. Not obvious to the naked eye from one night to the next, but obvious to precise observation over years and decades. NASA's Hubble material shows that Proxima has a relatively large proper motion and moves about 3.85 arcseconds per year across the sky. For a star, that is a strong clue that it is genuinely nearby. Distant stars barely seem to move at all in comparison. Proxima does. That changes the way you think about the night sky. The sky looks fixed when you casually look up, but the nearest stars are not fixed. They are moving, and Proxima is close enough that we can watch that movement with real data. Its path can be plotted, its future position can be predicted, its close passes near background stars can be forecast years in advance. That is not poetic language, that is observed astrometry, and that motion is scientifically useful. Because astronomers can predict where Proxima will pass in front of distant background stars, they can prepare for rare alignments and use effects like gravitational lensing to refine the star's properties and even look for hints of planets. So the nearest star is not just a point in the dark, it is a moving system with a measurable track, a measurable distance, and a measurable future position. That is one of the biggest shifts in modern astronomy. Nearby stars are no longer just lights, they are targets with geometry. So by this point, Proxima has already become much more than the nearest star. It is measured by parallax, tracked by proper motion, mapped with precision, and watched closely enough that its motion creates opportunities for new science. That should make the next turn hit even harder, because once the nearest star stops being just a light and starts becoming a real place, another question shows up immediately. If this star is real, nearby and measurable, then what makes it truly irresistible is not only the star itself, it is the fact that there is a world there. Proxima is not standing still, it is sliding across the sky, and that is one of the clearest signs that it is truly nearby. When people look up at the night sky, the stars seem fixed. They seem nailed into place, like a background that never changes. But that is only how the sky looks at casual human timescales. In real astronomy, the closer stars give themselves away by moving. NASA's Hubble material notes that Proxima has a relatively large proper motion compared with more distant background stars, and in time-lapse observations it does not stay frozen in one place. It drifts. That matters because it breaks one of the oldest instincts people have about the sky. The night sky is not a painted dome. It is not a flat ceiling of lights. The stars are moving through the galaxy, and the ones that are closest to us can be tracked well enough that their motion becomes obvious over years and decades. Proxima is one of the best examples of that. It is not a symbolic point in the sky. It has a path. It changes position. It can be watched. The number itself sounds tiny, but the meaning is huge. Hubble's Proxima material gives its proper motion as about 3.85 arcseconds per year. That sounds microscopic, and on a human visual scale it is. NASA even compares it to the angular size of a nickel seen from about 1.5 miles away. But this is not a nearby airplane or a planet in the solar system. This is a star, trillions of kilometers away, shifting against much more distant background stars by that amount every year. For something that distant to move that much on the sky is a strong sign that it is genuinely close on the galactic map. That is the point where the sky stops being decorative and becomes dynamic. Once you measure Proxima's motion, the nearest star is no longer just over there. It becomes an object with a track and a speed, moving through a field of background stars that are effectively much farther away. That is a major change in perspective. The sky looks still to the eye, but to precise instruments it is active, and the closest stars are the ones that make that activity easiest to see. And Proxima's motion did more than prove it was nearby. It created real scientific opportunities. Because astronomers could project its path so precisely, Hubble researchers were able to predict rare close alignments with background stars in October 2014 and February 2016. Those were not just interesting coincidences. They opened the door to gravitational microlensing measurements that could refine Proxima's mass and potentially reveal the influence of planets around it. That is a big step up in stakes. The nearest star is not only measurable, its motion actively sets up experiments in the sky. That is one of the strongest science beats in this whole story. Proxima is scientifically useful because it moves enough, and because we can track that motion precisely enough to predict when it will pass close to distant background stars. When that happens, gravity can bend the background starlight in subtle but measurable ways. So the motion is not just a curiosity, it is a tool. It lets astronomers turn geometry and gravity into a way of learning more about the nearest stellar system. This is where distance turns into dynamics. Once you measure Proxima well enough, it stops being a faraway light and becomes an active system with a past path, a future path and testable behaviour. It has a measurable history. It has predictable alignments. It has enough motion on human timescales that astronomy can build observations around where it will be years from now. That is one of the deepest shifts in modern astronomy. Nearby stars are no longer just points of light in a catalogue, they are moving targets with geometry and timing. And that shift matters because it makes Proxima feel more real, not less. The moment a star has a measurable track across the sky, it stops being abstract. It becomes part of a local map. It becomes something whose position changes enough that we can watch the local galaxy in motion. That is a very different emotional picture from the old idea of stars as fixed lights hanging motionless overhead. By this point, Proxima is already doing a lot at once. It is the nearest star, it is part of a stretched 3-star system, its distance is measured by parallax, and its motion is large enough that we can watch it drift across the sky and use that drift for real science. And once you know all that, the next turn becomes even more compelling. The nearest exoplanet story does not begin with a theory. It begins with a world that made this system impossible to ignore. The nearest exoplanet story starts with Proxima b, because the distance stops being abstract the moment there is a world attached to the star. Proxima matters partly because it is the nearest star, but it matters much more because it hosts a planet that immediately changes the stakes. NASA's catalogue lists Proxima Centauri b as a super-Earth with a mass of about 1.055 Earths, orbiting at about 0.04848 astronomical units, with a year that lasts only 11.2 days. That is the shift that makes the whole system feel real in a new way. The nearest star is no longer just a point of light. It is a place with a specific planet in it. And that one fact changes the emotional weight of the whole topic. You're no longer just asking how far away the nearest star is. You're asking how far away the nearest known roughly Earth mass world is. That makes the distance feel less like a number and more like a barrier standing between us and an actual destination. Proxima b turns the system from a geometry problem into a world problem. Then the phrase habitable zone shows up, and that phrase needs to be handled carefully. NASA and ESO both describe Proxima b as orbiting within the habitable zone of Proxima Centauri, meaning it sits at a distance where liquid water could be possible under the right conditions. But that phrase does not mean the planet is actually habitable. It does not mean there are oceans, air, weather, or life. It only means the energy coming from the star is not automatically disqualifying. That is a much narrower claim than people often hear, and that is where the stakes rise again. The nearest potentially temperate rocky world is not orbiting a calm, sun-like star at a comfortable distance. It is orbiting a red dwarf at point-blank range. NASA's exoplanet and atmosphere work notes that Proxima b sits in a region where it can be hit by extreme ultraviolet radiation hundreds of times stronger than what Earth gets from the Sun, with atmospheric loss potentially happening far faster than on Earth. So habitable zone here is not a comforting phrase. It is a warning label with one hopeful detail attached. Its short year tells you how alien the system really is. An 11.2-day orbit means Proxima b is hugging its star very tightly. This is not Earth moved farther out into the galaxy. It is a completely different orbital setup created by the fact that Proxima is much dimmer than the Sun. A planet has to get in very close to receive enough energy, and that closeness changes everything about the planet's environment. That same geometry is what makes the planet scientifically exciting and physically difficult at the same time. Because the orbit is so tight, researchers have long treated tidal locking, strong stellar weather exposure, and atmospheric erosion as serious issues in judging whether the planet could stay temperate over long periods. NASA and related habitability studies point directly to irradiation, volatile loss, and rotation state as central questions. So the nearest likely rocky exoplanet also becomes a lesson in how unfamiliar Earth-like can really be, once you look past the mass and the habitable zone label. That is why Proxima b turns the distance into a scientific obsession. Without the planet, Proxima would still be important as the nearest star. With the planet, the system becomes much harder to ignore. Now the question is not just whether we can measure the nearest stellar neighbour. It is whether the nearest potentially temperate rocky planet could still be hostile in ways that make Earth comparisons misleading. That takes the story out of abstract astronomy and pushes it straight into astrobiology, planetary climate, and the future of interstellar exploration. And once one planet is in the picture, the obvious next question starts building pressure immediately. Is Proxima just one famous planet around one nearby star, or is the whole system more crowded, messier, and more complicated than that first discovery made it seem? Then the system got more complicated than one Earth next door, and that is exactly what makes Proxima harder to ignore. It would already matter if it were just one nearby star with one famous planet. But the closer astronomers looked, the less simple the system became. ESO announced Proxima d in 2022, orbiting only about 4 million kilometers from the star, less than 1/10 of Mercury's distance from the Sun, and completing an orbit in just 5 days. That instantly tells you this is not a quiet system built around one lucky world. It is a tightly packed planetary system squeezed in close to a dim star. That matters because it changes the mental picture again. Proxima is not just a red dwarf with one headline planet sitting in the habitable zone. It is already a compact planetary laboratory with multiple orbital regimes packed into a very small region. One planet can circle in 11.2 days. Another can whip around in just 5. So the nearest stellar neighbour is not giving us a simple, clean target. It is giving us a system where the structure is still unfolding as the data improve. And that is not just old news. NASA's 2025 Alpha Centauri overview says Proxima has at least one planet, and possibly 2 more. A separate 2025 web-related release goes even further in its wording and refers to 3 confirmed planets orbiting Proxima Centauri. That is a very useful tension in the story, because it shows that even in the nearest stellar system, the details are still being refined, debated, and updated as observations get better. The local neighbourhood is not settled territory. We are still figuring out exactly what is there. That uncertainty is not a weakness in the science. It is part of the reality of exoplanet work, especially around an active red dwarf. The system is close enough to study in extreme detail, but also complicated enough that each new instrument can sharpen, revise, or complicate the picture. So when people talk about the nearest star system as though it is already fully mapped and understood, that is too simple. It is nearby, yes. It is measured, yes. But it is still revealing itself. Then there is the outer candidate world, often called Proxima C. Archive material in the NASA Exoplanet Archive describes it as a low-mass planet candidate orbiting at about 1.5 astronomical units from the star, much farther out than B or D. Whether that object fully survives future scrutiny is important scientifically, but even before that question is settled, the larger point is already clear. The closer we look at Proxima, the more the simple image breaks apart. Instead of one star and one nearby rocky planet, you start getting multiple worlds, candidate detections, disputed signals, and a system that refuses to stay tidy. That is one of the most honest lessons in this whole story. Nearby systems are messy. The nearest star is not automatically the simplest star. In fact, it may be the opposite. The fact that Proxima C remains discussed as a candidate rather than an easy closed case is part of that lesson. The system is close enough to tempt confidence, but complicated enough to force humility. We are still sorting signal from noise, planet from possibility, and stable picture from evolving one. And that is why the distance becomes more than just a source of frustration. Distance is terrifying, but complexity is what makes the trip worth imagining. A nearby star with nothing around it would still be scientifically important. A nearby system with a habitable zone world, a 5-day inner planet, a debated outer candidate, and a violent central red dwarf becomes much more than important. It becomes irresistible. That is where the stakes rise again. Proxima is not only hard to reach, it is rich enough to justify the obsession. The nearest star is already giving us multiple worlds, active debate, and a system architecture that keeps growing more interesting instead of less. That combination matters. When a target is both extremely difficult and scientifically loaded, it starts changing how civilization thinks about exploration. And then the story gets darker, because even if the system is full of interesting worlds, the star itself may be the biggest threat to all of them. The star itself may be the biggest threat to everything around it, and this is where the whole story changes tone. Up to this point, Proxima can sound like hope because it is close and because it has planets. Then you look at the star's behaviour, and the system starts looking hostile. NASA describes Proxima as frequently erupting in large and powerful flares, and a 2021 study highlighted one of the most extreme flares ever seen from the star across multiple wavelengths. This is not a calm sun with a quiet habitable zone. It is an active flare star with a violent magnetic temperament. That matters immediately for habitability. The nearest interesting world does not orbit a stable, gentle star. It circles one that repeatedly throws out bursts of radiation and energetic particles. NASA's 2025 Alpha Centauri overview says Proxima frequently erupts in intense ultraviolet radiation, and that this may be enough to strip away an atmosphere if a planet cannot hold on to it. So the nearest potentially temperate exoplanet may also sit inside one of the harshest nearby space weather environments we know. Around a red dwarf, the habitable zone is also the danger zone. Because Proxima is dim, the habitable zone sits very close to the star. That is why Proxima b is interesting in the first place. But the same geometry that puts a planet in the right temperature range also keeps it close to the source of flares, radiation, and particle storms. NASA's work on Proxima b says an Earth-like atmosphere there may not survive, with modelled escape rates ranging from the loss of an Earth-sized atmosphere in about 100 million years to about 2 billion years, depending on atmospheric conditions and magnetic protection. ALMA's 2025 flare study pushes that point even harder. The observatory reported that nearby habitable zone planets around Proxima could be rendered uninhabitable if repeated flares strip away ingredients such as ozone and water. The same release notes that Proxima's flare activity is extreme at radio and millimeter wavelengths too, not just in visible light, which means the system's violence is broader than a casual picture of just some bright flashes would suggest. The physics of the star helps explain why the system is like this. ALMA states that Proxima's small size and strong magnetic field indicate its entire internal structure is convective, unlike the Sun, which has both convective and non-convective layers. That is not a decorative stellar detail, it is part of why the star is so magnetically active. Its magnetic fields can twist, build tension, and snap, releasing energy and particles as flares. So the nature of the star itself may help decide whether nearby planets keep atmospheres, retain water, or lose the conditions needed for surface life. This is the real mood shift in the whole video. At first, Proxima looks promising because it is the nearest star with a potentially temperate planet. Then it starts looking like a trap, because the same close orbit that makes a planet warm enough may also expose it to constant assault. NASA and ALMA together point to the same basic conclusion. A planet can sit in the habitable zone of a red dwarf and still face atmospheric erosion, ozone loss, water loss, and long-term chemical damage from the star itself. And that is why Proxima breaks the lazy version of just find another Earth nearby. The nearest red dwarf system does not greet us with familiarity, it forces a harder question. If the most common stars in the galaxy are active red dwarfs like this, then reaching them is only one problem. Surviving what they do to their planets may be the bigger one, and the story still is not finished because even the route into the system may not be clean. Proxima is not only violent, but likely surrounded by debris that could turn a fast arrival into an impact nightmare. The road to Proxima is not empty, and that changes the mission picture right away. In 2017, ALMA detected coal dust around Proxima Centauri, including a belt extending roughly 1 to 4 times the Earth-Sun distance from the star. That is not just a nice extra detail for astronomers. It means the system is not a clean target with one star and one famous planet. It has leftover material, debris structures, and signs that the architecture may be more elaborate than the simple one-planet version people first picture. That matters because dust belts are evidence of history. They are the remains of material that did not end up inside planets. ESO describes them as particles of rock and ice ranging from sub-millimeter dust grains up to asteroid-like bodies many kilometers across. So when you say there is dust around Proxima, you are not talking about a soft haze in the abstract. You are talking about a spread-out field of material that tells you the system formed, collided, evolved, and likely still contains more structure than we have fully mapped. The belt is cold, real, and massive enough to matter. ESO reported the dust belt at about minus 230 degrees Celsius, with a total mass of around 1/100th of Earth's mass. That number can sound small at first, but the important point is that it is not one object. It is a distributed population of particles and bodies spread through space. For astronomy, that is a clue to the system's formation history. For exploration, it is a hazard map. And the hazard part matters more the faster you try to go. In ordinary thinking, dust sounds harmless. At interstellar speeds, it is not. Even tiny particles become dangerous when the closing speed is high enough. That is why ESO explicitly linked knowledge of Proxima's dust environment to future mission planning, including Starshot-style ideas using laser-driven microprobes. The moment you start talking about meaningful fractions of light speed, sparse material stops being background and starts becoming impact physics. Then the picture gets more complicated. ALMA's data also hinted at an even colder outer dust belt much farther out, roughly 10 times farther than the inner one if the signal is real. Even as a tentative result, that pushes the system farther away from simplicity. The nearest star is not only far and not only active, but possibly cluttered as well. Reaching it would not just mean surviving the crossing, it would also mean arriving in an environment that may contain dust, debris, and bodies we have not fully catalogued. That is the deeper tension in this section. The closer Proxima gets to being a real destination, the less clean it looks. First it was just a nearby star, then it became a system with planets, then it became a flare-prone red dwarf system with planets. Now it is a flare-prone red dwarf system with planets and debris. Every layer makes it more scientifically valuable, and every layer also makes it harder to reach safely. So dust changes the tone in a very practical way. It takes interstellar travel out of pure propulsion talk and turns it into collision planning. A tiny grain at very high speed is not a minor nuisance. It can be mission-ending. That is true during the crossing, and it is also true when you enter a system that may not be empty. So the nearest star is not just distant, it is guarded by impact risk both on the way in and once you get there. And that makes the next point hit even harder. Humanity's farthest spacecraft feel heroic inside the solar system, but against Proxima, even those achievements barely count as leaving home. We have barely left home, and that should scare you. Voyager 1 is in interstellar space, and it is still almost nowhere compared with Proxima Centauri. NASA says that as of August 21st, 2024, Voyager 1 was about 164.7 astronomical units from Earth, making it the farthest human-made object ever sent out. That is an extraordinary achievement by solar system standards. It crossed the heliosphere, it kept going, and it reached a distance that would have sounded impossible a century ago. But once you put that next to Proxima's roughly 268,770 astronomical units, the picture changes completely. Voyager has covered only a tiny fraction of the gap. Even our deepest probe is still pressed against the edge of home. That comparison is the punchline people usually avoid. We like to say Voyager is in interstellar space, and that is true in the technical sense, but technical truth is not the same as emotional truth. Emotional truth is that Proxima is so far away that Voyager's distance, as historic as it is, barely registers against the full crossing. The farthest machine we have ever built has not begun to solve the interstellar problem. It has only shown how large the problem really is. New Horizons gave us a dramatic perspective shift, not a starship revolution. NASA's 2020 parallax experiment showed Proxima from a vantage point more than 7 billion kilometers or 4.3 billion miles away from Earth. That is amazing science. It is enough distance to make the star visibly shift against the background, which is a beautiful demonstration of how we measure stellar distance. But it is also a reminder of how little of the road we have crossed. Billions of kilometers sound enormous, until the target sits tens of trillions of kilometers away. That is why interstellar distance is so hard to feel correctly. A mission like New Horizons really did go deep into the outer solar system. It really did change the viewing geometry enough to make parallax visible. That is a major scientific achievement. But against Proxima, it still looks like the first step off the porch. The mission is impressive, the baseline is huge, and the target still makes both of those things look small. The solar system is huge, but Proxima dwarfs it anyway. That is one of the most important turns in the entire story. You first learn that the outer planets are far away, that the Kuiper belt is remote, that the heliosphere reaches into a vast region beyond the known planets, and that deep space missions are hard won. All of that is real. None of it is exaggerated. But then Proxima shows up and forces a second correction. All of that vastness is still local. It is still the neighbourhood around one star. That is the part that should land hardest. The terrifying thing is not that humanity has gone nowhere. The terrifying thing is that what we call far was never remotely far enough. Voyager, New Horizons, the giant planets, the edge of the heliosphere, all of that still belongs to the first layer of the map. Proxima is outside that layer. It is where the scale changes so hard that every deep space triumph starts to look like a prologue rather than the main event. Interstellar travel begins where our current triumphs end. That is the real escalation here. Every mission you admire for reaching the deep solar system is still part of the pre-interstellar era. These missions taught us how to survive launch, navigate across planetary distances, use gravity assists, manage power over decades, and keep machines alive in deep space. Those are major achievements. But the distance to Proxima forces a much harsher conclusion. Humanity has only mastered interplanetary travel in the loosest possible sense and has not yet seriously entered the interstellar era. That is why Proxima is such a brutal benchmark. It is close enough that we can measure it beautifully, model it, track it, and study its planets. And at the same time, it is far enough to expose how young our technology still is. The nearest star is not only a destination, it is a test that current civilization still fails by a very wide margin. And once that is clear, the next problem gets even worse. The barrier is not just that our rockets are too weak. The barrier is that the energy bill for crossing interstellar space is so severe that build a bigger rocket stops sounding serious. The rocket problem is not just engineering, it is energy tyranny. You do not just build a bigger rocket for a 4 light-year trip. Once your target still needs tens of thousands of years at Voyager-class speed, the problem stops looking like an upgraded mission and starts looking like a different branch of physics and engineering. Breakthrough Starshot says it directly. With current spacecraft speeds, reaching Alpha Centauri would take tens of thousands of years, and in broader discussions of conventional propulsion, the timescales stretch into tens or even hundreds of millennia. That is the sentence that should land hard, because it strips away the comfortable idea that interstellar travel is just one more engineering step after Mars. The real barrier is carrying enough energy and throwing enough mass. Every extra kilogram you want to accelerate to extreme speed costs energy. Every tank of propellant has to help move the rest of the propellant. NASA propulsion material and interstellar propulsion studies keep coming back to the same core issue. The rocket equation punishes you as the mission velocity rises, because onboard propellant becomes part of the mass burden you're trying to accelerate. That is why brute force does not save you. You do not need speculative language to make that feel severe. You just compare present spacecraft performance with Proxima's distance and watch the mass and energy demands explode. That is exactly why serious interstellar discussions move so quickly away from ordinary rockets. They jump to beamed propulsion, fusion, or other non-standard architectures, not because scientists want exotic ideas for style points, but because standard propulsion leaves you trapped in absurd mission durations. NASA work on advanced propulsion says that for interstellar flyby missions near 1/10 of light speed, concepts using onboard propellant would need extremely high specific impulse, far beyond conventional systems, while beamed energy approaches have the advantage of offloading much of the propulsion system mass from the vehicle. Breakthrough Starshot makes the same choice for the same reason. Cut the craft down to gram scale, leave the energy source at home, and push with a light beam. That is the moment where the problem stops feeling like missing technology and starts feeling like hard terms set by nature. Distance, mass, velocity, and energy are not negotiable. Even the minimum energy floor rises brutally with speed, and studies of propulsion energy note the basic point very clearly. Double the spacecraft mass and the required propulsive energy at least doubles. Double the speed and the required energy at least quadruples. before you even pay for inefficiencies and propellant overhead. Proxima Centauri is where that becomes emotionally obvious. The universe is not asking for a slightly better engine. It is asking for an energy bill so large that modern civilization still does not know how to pay it in a practical way. And once that lands, the next temptation appears immediately. People hear those numbers and think maybe relativity can rescue the whole story. Maybe if you go fast enough, time itself starts helping you. And that is where the next section gets dangerous, because relativity helps a little and humiliates you anyway. Relativity helps a little and humiliates you anyway. Once you hear that Proxima is 4.25 light years away, the obvious next thought is simple. Go fast enough and let time itself help you. That instinct is not wrong, but it is incomplete. Relativity does change the onboard experience for a traveller moving at a large fraction of light speed. NASA's relativity material explains the core idea clearly. As you move faster and approach the speed of light, time slows down relative to people in another frame, and distances along the direction of motion are effectively shortened for the traveller. But that is not a cheat code. It is a partial mercy laid on top of a mission that is still extreme by any normal standard. At 1/5 of light speed, the trip is still a generation-scale technological act. Breakthrough Starshot's concept targets about 20% of light speed, and its own materials say a flyby mission could reach Alpha Centauri in just over 20 years after launch. That sounds miraculous only because current spacecraft are so slow. 20 years is still not a casual mission. It is a multi-decade commitment just to get there. And because Proxima is about 4.25 light years away, the data would still need more than 4 additional years to get back to Earth at light speed. Even your breakthrough scenario still forces patience on the scale of careers and eras. And if you go slower, the optimism collapses fast. At 10% of light speed, the crossing time is still on the order of 42 years before any return signal. Drop far below that and the travel time climbs hard. Go back to current probe speeds, and you are right back in the tens of thousands of years. That is the real lesson here. Interstellar missions are not linearly harder than planetary missions. They are categorically harder. Small changes in velocity decide whether you are talking about one working lifetime, several generations, or spans of time so long that the mission stops feeling connected to the civilization that launched it. And relativity does not rescue the people waiting at home. Even if time aboard a near-relativistic probe is kinder to the travellers, or to the onboard systems in a frame-dependent sense, Earth still waits through decades, and communication still cannot outrun light. NASA's relativity explanations make that limit clear. Nothing with mass reaches the speed of light, and light remains the maximum speed for information. So relativity gives you a little hope and a very sharp betrayal at the same time. It says the travellers may experience less time. It also says everyone they report to stays trapped on the far side of the same delay. Distance still wins, it just wins more elegantly. And once that is clear, the next problem becomes unavoidable. Even if you could cross the gap fast enough, putting humans on that mission turns the distance into something even worse than a propulsion problem. It turns it into a survival problem. A human mission turns distance into a survival problem. The moment you put people on board, every engineering problem becomes biological. Robotic probes can be tiny, cold, silent, and patient. Humans cannot. NASA's Human Research Program reduces long-duration spaceflight to a set of core hazards, and they are exactly the kinds of problems that get worse, not better, when the trip is long. Radiation, isolation and confinement, distance from Earth, gravity or lack of it, and closed or hostile environments. The moment you imagine humans crossing 4.25 light years, the mission inherits shielding, food, water recovery, air recycling, behavioural health, redundancy, medical response, and failure recovery as survival requirements, not nice extras. That is what makes a crewed Proxima mission so different from a robotic one. NASA's life support work is built around open and closed-loop systems precisely because long missions need to recycle air and water, control contamination, manage waste, and keep the cabin environment stable for a very long time. NASA's human health guidance also notes that long-duration missions drive extra needs for privacy, volume, and behavioral support because confinement, stress, and isolation directly affect performance and safety. So the distance to Proxima is not only asking how to get there, it is asking how to keep fragile organisms alive and functional while civilization changes behind them. Current spacecraft timescales make crewed travel absurd immediately. At Voyager-class speed, you're not talking about a voyage, you're talking about roughly 75,000 years. At Parker-class peak speed, you're still talking about roughly 6,500 years, and that speed is not even a real interstellar cruise profile. Those numbers alone kill any near-term crewed fantasy built on present propulsion. Before you get to biology, governance, or ethics, the timeline already breaks the plan. The ship would outlast nations, institutions, and probably entire branches of culture. And even a fast human mission would rewrite what a mission is. Suppose one day propulsion reaches serious fractions of light speed. You still would not get a normal expedition. You would get a mission where launch and arrival are separated by decades, with no live control and no rescue in any meaningful sense. NASA's human spaceflight risk framework treats distance from Earth itself as a core hazard, because as distance grows, communication delay, limited resupply, limited evacuation, and delayed medical support all become central constraints. A crewed interstellar mission would push that to the limit. That is not Apollo scaled up. That is a civilizational project that has to outlast leadership, institutions, and maybe even the culture that began it. This is why most realistic first contact dreams are robotic. Robotic systems are ruthless in the best way. They can be miniaturized, tolerate silence, survive one-way risk, and operate without comfort, rescue, or morale. Humans cannot do that. NASA's spaceflight hazard material makes the contrast very clear without trying to. Radiation is hard to shield, isolation affects behavior, distance cuts off support, and hostile closed environments add constant failure pressure. A robot can accept that kind of mission much more easily than a human body and mind can. So the distance to Proxima forces a painful but mature conclusion. If humanity ever sends something there, the first thing is overwhelmingly likely to be machine intelligence, instrumentation, and automation. Not because that is less inspiring, but because the numbers do not care about romance. They care about mass, radiation dose, life support closure, system reliability, and survival time. And that pushes the first real interstellar attempt away from human passengers and toward ultralight, highly autonomous probes instead. And that leads directly to the next escalation. If human crews are too fragile for the first crossing, then what does a serious robotic attempt actually look like when people stop pretending normal rockets are enough? Breakthrough Starshot is what serious desperation looks like. It exists because the normal options are hopeless. Once researchers ran the numbers honestly, the conclusion was brutal. Current rockets do not get you to Alpha Centauri on meaningful timescales. Breakthrough Starshot's own material says that with today's fastest spacecraft, the trip would take about 30,000 years. That is why the project does not try to slightly improve the old model. It throws the old model away. The concept uses a ground-based light beamer to push ultralight light cell nanocraft to about 20% of light speed, roughly 100 million miles per hour. That is what taking the nearest star seriously looks like. The concept is tiny probes, extreme speed, and almost no margin. Starshot is built around gram-scale robotic nanocraft and meter-scale sails. The whole point is to stop hauling huge fuel tanks through space. Instead, you strip the payload down to almost nothing and leave the energy source at home. The project describes a starship carrying cameras, power, navigation, communication, and other systems on a gram-scale platform attached to a light cell made from ultralight materials. That is not a stylistic choice. It is what the distance to Proxima forces when the difference between current travel times and useful travel times is not a little improvement, but a collapse from tens of thousands of years toward a few decades. And the project is honest about the nightmare list. Breakthrough Starshot does not pretend this is easy. Its concept material openly lists the major barriers: building a ground-based kilometre-scale light beamer, generating and storing a few gigawatt-hours of energy per launch, correcting for atmosphere with adaptive optics, accelerating each nanocraft to target speed within minutes, surviving interstellar dust collisions, and then sending scientific data back across light years with a compact onboard laser communication system. That honesty is why the concept matters. It is exciting precisely because it does not hide how violent and unforgiving the crossing would be. And if it works, it changes the history of the species. That is not hype. A successful Starshot-class mission would mean humanity had crossed from interplanetary capability to interstellar capability in a real sense. Not with a crew, not with a colony ship, but with our own hardware entering another stellar system and sending information back. The first images of planets around another star taken by a probe we built would not just be scientific results, they would prove that the stars are difficult rather than forbidden. That is why Proxima is so loaded. It is the nearest place where that line could actually be crossed. And even then, the next problem is waiting. Going fast enough to make the trip possible creates a new problem that is almost as cruel as the distance itself, because reaching Proxima is only half the problem. Arriving is worse. Reaching Proxima is only half the problem, arriving is worse. At Starshot-style speeds, you do not really arrive at Proxima in the way people normally mean arrival. You do not slow into orbit. You do not settle in and begin a long survey. You blast through the system in a high-speed flyby. That is one of the hardest things to accept about interstellar travel. The faster you go, the better your travel time gets, and the worse your arrival becomes. Velocity solves one problem and creates another. Breakthrough Starshot is designed as a flyby for exactly that reason. Because getting to about 20% of light speed is already hard enough, and slowing down is a separate challenge on top of that. That changes what a successful mission even looks like. A flyby probe does not get months or years to study the system the way a Mars orbiter or a Saturn mission can. It gets a brief pass. The scientific value depends on autonomous targeting, burst imaging, onboard timing, hardened systems, and the ability to grab as much meaning as possible in a very short window. At Proxima, a first fast mission would be less like ordinary exploration and more like a precision strike for data, where everything has to work during a tiny slice of time after a journey of decades. That is a radically different style of exploration from what people are used to in the solar system. And that is why slowing down deserves its own place in the story. Interstellar travel is not one breakthrough, it is at least two. First, accelerate to useful speed. Then survive and decelerate in a way that still leaves you able to do serious science. The distance to Proxima hides that twist very well. At first, speed looks like the whole answer. Then the moment you start talking about arrival, you realise too much speed can rob you of the destination. Some studies have explored ways a light sail might break using radiation pressure and gravity in the Alpha Centauri system, but those concepts require very different sail properties and much longer overall trip times than a simple Starshot-style flyby. So Proxima turns success into a more difficult version of failure. A slow mission takes too long to matter on human timescales. A fast mission may only get a glance at the target. That is the cruel symmetry here. The nearest star does not merely demand a new engine, it demands a new philosophy of exploration. Where getting there and being able to do science there are separate mountains, and both are steep. And that is exactly why Proxima remains the best target anyway. Because even with all these problems, nothing else makes more sense as the first real step beyond the Sun. And yet Proxima is still the best target we have. Because even with all the problems, nothing else makes more sense. It is the closest star inside the closest stellar system, with known planets and active discoveries still coming in. If you want to test whether interstellar exploration is possible at all, you do not pick the prettiest target, you pick the least impossible one. That is exactly why Proxima and the wider Alpha Centauri system keep coming back in both real astronomy and serious mission concepts. NASA's 2025 overview of the system makes that clear. Proxima is our nearest stellar neighbour, part of the nearest triple star system, and it has at least one planet with possibly two more. And the whole Alpha Centauri system is now scientifically exploding with value. In August 2025, NASA reported that Webb had found the strongest evidence yet for a gas giant candidate orbiting Alpha Centauri A, the closest Sun-like star to Earth. If confirmed, that would mean the nearest stellar neighbourhood is not just one red dwarf with one famous rocky planet. It is a system where multiple stars may host worlds, some rocky, some giant, some confirmed, some still emerging from the data. That turns the nearest system into a full exoplanet frontier, not just a single headline object. That is why Proxima is such a powerful target. Distance and scientific payoff scale together here. The closer the system is, the easier it is to study in finer detail, and the easier it becomes to justify future direct exploration. Every planet found there increases the value of the target. Every flare, dust belt, and orbital clue makes the system more difficult and more irresistible at the same time. NASA's current material already frames Alpha Centauri and Proxima as a nearby system with multiple possible worlds and unusual scientific leverage, simply because of how close it is to us. So by this point, Proxima is not just one star among many. It is the threshold object. It is where astronomy, propulsion, astrobiology, autonomy, communication delay, and long-term civilizational planning all collide in one place. The terrifying distance matters because it defines the opening move of any future beyond the solar system. And that is exactly why the ending has to land hard, because Proxima is close enough to tempt us, and far enough to break us. Proxima is close enough to tempt us, and far enough to break us. That is the final point. The nearest star proves the galaxy is both accessible and almost unreachable at the same time. Proxima is not some fantasy object hidden on the far side of the Milky Way. It is local, it is measured, it is mapped, it is moving, it has planets, it flares, it has dust. It is a real nearby system that modern astronomy can study in detail. And still, with current spacecraft speeds, the trip remains measured in thousands to tens of thousands of years. Voyager-class travel is on the order of about 30,000 to 75,000 years, depending on the assumptions, and even radically faster concepts are still multi-decade missions at best. The galaxy is not forbidden. It is just priced far above what our current technology can actually pay, and that forces you to redefine what progress means. A mission to Proxima would not be one more step in the same line from the Moon to Mars to the outer planets. It would be a rupture in history. It would mean moving from missions you can supervise directly to missions that must operate on their own, survive alone, and send results back across years of silence. Breakthrough Starshot's own concept only works by accepting that reality up front. Tiny autonomous probes, extreme speed, flyby science, and delayed return of data years after arrival. So the terrifying distance to Proxima is really the terrifying distance between our current civilization and the next form it would need to become if it ever wanted to cross interstellar space in a serious way. And the science has already destroyed the old idea of empty nearby space. The nearest star system is not blank. It is already a real astrophysical arena. Proxima is a faint red dwarf in a triple star system with Alpha, Centauri A and B. It hosts at least one well-known Earth mass planet, likely more than one world in the system, strong flare activity and dust structures that point to a more complicated formation history. Webb has even added evidence for a giant planet candidate around Alpha Centauri A, which means the nearest stellar neighbourhood keeps getting richer the closer we look. So the stakes are not abstract anymore. There is already enough in this system to transform astronomy. The only open question is whether we will ever close the gap with hardware instead of telescopes alone. That is why Proxima Centauri is terrifying. Not because it is the farthest thing, but because it is the nearest thing that still makes human ambition look small. It strips away the comforting language. It crushes ordinary engineering. It shows you that a nearby habitable zone planet can orbit a violent red dwarf. It shows you that even the nearest stellar system is stretched across enormous separations, and it still stays close enough to make you want to try. That is what makes it so hard to ignore. Proxima is the point where the universe stops sounding merely large and starts feeling resistant. And once that really lands, you understand why the first true trip to another star would not just be another mission, it would change what we mean by civilization. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.